Morning, ma'am.
Good morning. Can you hear me?
Yes, ma'am.
For a reaction, AA plus BB in equilibrium with CC plus DD, there is forward reaction and there is backward reaction. The rate of forward reaction, the speed of forward reaction that depends upon the concentration of the reactants. That is proportional to concentration of the reactants to the power its stoichiometric coefficient, A to the power A and B to the power B. B to the power B. And rate of backward reaction is proportional to, or you can write RF is equal to a constant Kf into A to the power A and B to the power B. Rate of backward reaction, that is rate of backward reaction, RB, rate of speed of backward reaction. That is proportional to backward reactions, that is concentration C to the power C and D to the power D. Or RB is equal to KB into C to the power C into D to the power D. So this is RF and this is RB, rate of backward reaction. At equilibrium, rate of forward reaction becomes equal to rate of backward reaction. That means Kf into A to the power A into B to the power B is equal to Kb into C to the power C into D to the power D. So I am going to write that Kf is equal to Kb at equilibrium. At equilibrium. Equilibrium means when the rate of forward reaction becomes equal to rate of backward reaction, we don't see, we don't observe, we don't find any, we don't feel any change in concentration as if it is still, but it is dynamic. It is moving that side, it is moving this side. That is Kb into C to the power C into D to the power D. Or Kf by Kb. What is Kf? I can take this Kb. So I can take this side to that. That is A to the power A into B to the power B. So Kf by Kb, a constant upon another constant, is a new constant. I am writing it as Kc. Kc, this is the equilibrium constant, which is equal to C to the power C into D to the power D upon A to the power A into B to the power B. This is known as law of chemical equilibrium. Kc is a constant. It is known as law of chemical equilibrium. which is known as law of chemical equilibrium. Write down. At a given temperature, the product of concentrations of the products raised to their stoichiometric coefficient of a balanced chemical equation divided by the product of concentrations of the reactants raised to their respective stoichiometric coefficient has a constant value. Write down. At a given temperature, the product of multiplication, the product of concentrations of products raised to their respective stoichiometric coefficient in the balanced chemical equation, divided by the product of concentrations of the reactants, raised to their respective stoichiometric coefficients. Has a constant value. This is known as law of chemical equilibrium. For example, 4NH3 gas plus 5O2 gas equilibrium 4NO gas plus 6H2O gas. In this case, the equilibrium constants, write only the concentration of gases and aqueous. Solids and liquids, you just neglect. There is no change in concentration of solids. There is no change in the concentration, or the change is negligible in the case of liquids. So you have to put only the aqueous and gaseous states. Here all are in gaseous state. So I am including all in that Kc. Kc is equal to NO to the power 4 into H2O concentration in equilibrium to the power 6 divided by remaining concentration. In the beginning, what concentration you are taking NH3, that much concentration will not be there in equilibrium. It will be less. So the remaining concentration of this NH3 to the power 4. Similarly, oxygen, reactant, it is reactant. In the beginning, how much oxygen you have taken, that much oxygen will not be there in this equilibrium. Some got reacted and gone to that side. So O2 to the power 5. This is the expression for this equilibrium constant. What is the need of this equilibrium constant? Looking at this equilibrium constant, suppose it has got a higher value. Higher value means numerator is more. That means product is more. We are getting more product. Suppose Kc has got very less value. That means reactant amount is high. Such a reaction is not useful. It is not advantageous because the amount of reactant we put, that is remaining like that only. Product is very less. So to make such reaction, it is not useful. So if Kc of a reaction is very high, that means it is a useful reaction, means we are getting more amount of products. Numerator will be high. That's why the Kc value is high. Okay, so Kc has got some implications, its importance. So Kc you can write in this format, aqueous and gaseous state you can put in this thing. Solid and liquid you can just avoid, neglect, because there is no change in the concentration of solids and liquids. Next equation I am giving. H2 plus I2, H2 gas plus I2 gas, which is an equilibrium with 2Hi, 2Hi. Kc. Kc is equal to, see we started from H2 and I2. So we say Kc for forward. Kc is equal to Hi square upon H2 raised to 1 and I2 raised to 1. All are in the gaseous state, and so I am putting all in this equilibrium equation. Kc, this is the combination combining H2 and I2 to form Hi. We started with H2 and I2 and we are getting 2 twice Hi. Now you consider its opposite way, that is decomposition of Hi to H2 and I2. Decomposition, that is 2Hi equilibrium. We started with 2Hi and we got H2 gas and I2 gas. The equilibrium constant for this. Its equilibrium constant, that is, I am writing Kc I am not writing because Kc for Kc it is Hi square. So I am writing K dash C, which is equal to H2 into I2 upon Hi square. See, this is the inverse of Kc. So K dash C, that is the equilibrium constant for the reverse, that means decomposition. This is combination, this is decomposition. So equilibrium constant for the reverse reaction of this, that is 1 by Kc. K dash C is equal to 1 by Kc. See, Kc is that much. This is K dash C. So for combination, if this is Kc, for decomposition, it will be just inverse of that, that is 1 by Kc. If I write this equation in this format, that is, I am taking this, instead of this 1, I am taking half. This is half H2 gas and half I2 gas, giving, then it is 1 Hi, that is Hi gas. See, I multiplied everything with what? Half. I multiplied every stoichiometric coefficient with half. Now the new equilibrium constant K2 dash C will be Kc raised to the number by which I have multiplied, that is half. The number by which I have multiplied, that is half. Let's see how it is coming. K2 dash C. K2 dash C. Okay, here the equilibrium constant K2 dash C is equal to Hi divided by H2 raised to half and I2 raised to half. This is K2 dash C. I can write this what? 2 into 1 by 2. 2 into 1 by 2. That is 1 only. Or I'll write half into 2. 1 only. So all these half I'll be putting inside one big bracket, that is Hi upon H2 into I2 whole to the power, this is square Hi square H2 into I2 whole to the power 1 by 2. Whole to the power 1 by 2 means I put those much portion for what is for Kc, normal Kc I put inside the bracket, which is equal to Kc to the power half. What is Kc? Kc is for H2 plus I2 giving 2Hi. So by which number you are multiplying this whole equation, that number will be coming on the top. That is K2 dash C is equal to Kc to the power half. Write one question. The following concentrations were obtained. The following concentrations were obtained the following concentrations were obtained. For the formation of NH3, from N2 and H2, N2 gas, H2 gas, at equilibrium, N2 and H2 at equilibrium at 500 Kelvin. So after balancing, we need a stoichiometric coefficient for balancing of equation is a must. That is N2 plus 3H2 gives 2NH3. Let it be that only. Now at equilibrium, they have given the concentrations of various species. N2 concentration. I am writing here N2 concentration. Concentration is always put in the square bracket. Concentration is put always in the square bracket. N2, that is 1.5 into 10 to the power minus 2 molar. Then H2, that is 3 into 10 to the power minus 2 molar. And NH3, that is in the equilibrium. Remaining N2, remaining H2, and the amount formed that is present in the equilibrium, which is equal to 1.2 into 10 to the power minus 2 molar. Now, question is calculate the equilibrium constant. Calculate the equilibrium constant. Calculate the equilibrium constant. This is the balanced equation. From this, you write the equilibrium constants, that is Kc is equal to NH3 whole square divided by N2 into H2 to the power 2. Now you substitute these values, substitute all these values. That is NH3, 1.2 into 10 to the power minus 2. That is 1.2 into 10 to the power minus 2 whole square divided by N2. That is 1.5 into 10 to the power minus 2. H2 square, this is H2. 3 into 10 to the power minus 2 raised to 3. 1.2, this dot is not visible. Can you see that? See, can you see this point? Anybody please respond to me. Can you see this one point? Can you see?
Yes, ma'am.
The point clearly. Means I am talking about this point, 1.5.
Yes, ma'am. We could see that.
Okay. But when I look into this screen, I cannot see that point. Now, if I okay, now I can see. So previous dot, what was there, I could not see on the screen. When I look into the screen, it all get faded type. You are getting it clearly. Okay. So after calculation, you will be getting some value. That is NH3 square, N2 into H2 cube. H2 to the power 3. So here the value we are getting is 0.106 into 10 to the power 4. 10 to the power. This is the equilibrium constant Kc. Why do we need Kc? Kc, looking at the Kc value, we can see that whether a reaction to be done in a factory or not. We are doing many reactions to make fertilizers. Early in the morning, we are putting this reactants. And after the day gets over, suppose you are not getting the products, and what is the use of spending this much money and doing this much work? So we are always looking for a reaction whose Kc value is very high. Means the amount of product should be very high. Is it advantageous to conduct a reaction, to do a reaction? First check the Kc value. Kc values of different reactions are given at a particular temperature. Okay. Next, we are going to another equilibrium constant, which is denoted by Kp. Kp. Here Kc, in Kc we are putting the concentration, molar concentration, moles per liter. But when all the species are in the gaseous state, then we can avoid this moles per liter. You can use pressures of these different species. Concentration of this, instead you can take pressure, because pressure measurement is very easy. Pressure of gas can be measured very easily. Suppose all are in the gaseous state, reactants and products, suppose all are in the gaseous state, we just avoid this concentration in terms of moles per liter. Instead, you can put pressure. But pressure is not concentration. Pressure is not concentration, but pressure is proportional to concentration. So instead of this molar concentrations, we are going to replace these by pressure. Pressure measurement is very easy. You know that. Sometimes we check the pressure of the gas, pressure of the air inside the tire, your car tire or scooter tire. It is very easy to measure. When you go to the petrol pump, sometimes we measure the pressure also, pressure of the tire or the wheel. So if all are in gaseous, since pressure measurement is very easy, we are not going to this concentration terms, because pressure measurement is very easy. And this pressure, gas means pressure, pressure means gas. Gas means, the term that is coming to our mind should be pressure. Gas means pressure. Pressure means everything of that gas. So, see, in the gas cylinder what you are using at home, sometimes you check by pressing the knob on the top. So if the gas is more, if the concentration of the gas is more, then when you press the knob, you will hear the voice, the sound. If that sound is there, okay, enough gas is there. If that sound is not there, gas is not there. Or that depends upon that sound. You can make out that how much pressure is inside. Means you can get an idea of the concentration, the amount of the gas inside the cylinder. So we are going to replace this Kc in terms of Kp. Kp is not equal to Kc, but Kp is proportional to Kc. So now we are telling gas means pressure, pressure means gas. Here, I'm taking one equation, that is N2 plus 3H2 gives 2NH3. N2 plus 3H2 gives 2NH3. Gas, gas, gas. Kc is equal to NH3 whole square divided by N2 into H2 cube. This is Kp. This is Kc. This is Kc. Concentration of a gas can be converted into pressure by using PV is equal to nRT. PV is equal to nRT, or P is equal to N by V RT. P is equal to this. N by V means number of moles in 1 liter. V is in the denominator in that much volume. So P is equal to CRT. C means the concentration. C means the concentration. So pressure of a gas can be written like this: its concentration into RT. So I'm going to write that concentration of NH3 into RT whole square divided by concentration of N2 into RT into concentration of H2. Yes, C, I'm writing the C, concentration. H2 into RT cube This is Kc. This concentration I am changing in terms of pressure, then I'll write it as Kp. Kc is this thing. Now I am writing what? Kp. Kp, that means pressure, pressure of this gas, pressure of this gas, pressure of this gas. Kp means pressure, pressure, pressure. Pressure I am writing in this way. So this is new term is Kp. Kc we have already written. Kp in terms of pressure we have written. So from here NH3 square, I am changing this NH3 square, RT square, then this RT, then H2 cube, and here RT cube. RT cube. This much portion, that means NH3, this much portion, NH3 square upon N2 into H2 cube is Kc. Kc. Then RT raised to 2, RT raised to 4. So these things will get cancelled and finally you'll be getting RT raised to minus 2. So here Kc into RT to the power, here it is 2, here 3 plus 1, 4. So denominator, in denominator twice, so it will be minus 2. So Kp is equal to Kc into RT raised to minus 2. There is a relation between Kp and Kc. So this is a gaseous state reaction. First we wrote Kc, but we said Kp is better because pressure measurement is easy. So I am writing Kp. Kp is written in terms of pressure, and in that I put Kc. So Kc into RT raised to minus 2. How you got this minus 2? You can take from here. See, 1 plus 3, that is 4. This is 2, altogether 2. Here altogether 4. That is products, number of moles of products minus number of moles of reactant. 2 minus 4, that is minus 2. So we can generally write it as delta N. You can generally write it as delta. So what is the relation between Kp and Kc? Kp is equal to Kc into RT raised to delta N. Delta N is what? Number of moles of gaseous products minus number of moles of gaseous reactors. Solid and liquid, there is no change. So only in the gaseous state. Okay, so that's the relation between Kp and Kc. Don't get confused. Kp is equal to Kc into RT raised to delta N. ऐसा नहीं है, Kc is equal to Kp into RT raised to delta N. So Kp is equal to Kp into Kc. Kp is equal to Kc into RT raised to delta N. Thank you.